exam Yeah, good afternoon, students. Today we are going to discuss about the year third year, sixth semester, digital electronics and communications. Okay, so in this digital electronics and communication systems, we must go for the year. Four blocks are there. One is the operational amplifier, first block, and in second block measuring instruments, and third block is the digital electronics, and fourth one is the modulation and demodulation. Okay, so let we go for the first one is the operational amplifier. Here also it may be divided into three units. So one is the differential amplifier and operational amplifier and its characteristic parameters, and third one is also op amps gear configuration and analysis. Okay, in detail we will discuss about the operational amplifier. So first of all, let you know about the what do you mean by amplifier. Okay, amplifier which is going to be strengthen the weak signal. Strengthen the weak signal. Okay, that means here it is going to be amplifies the signal here. So there itself, first of all, first one is the difference amplifier. That is a differential amplifier. So in this, let me go for the first of all, one of the useful and popular amplifier configuration, which is nothing but a differential amplifier, which is a direct coupled amplifier. Coupling means two. It is going to be required here. So in this, it is going to be accepting the two input signals and the output voltage, which is proportional to the difference between the two input signals. Okay, whenever you are feeding such a signal through an input section, so we are going to be taking the output as here, whether the signal is going to be amplified or not, which is going to be checking out by connecting to the voltmeter or else the ammeter. There itself you can able to observe that whether the signal is going to be amplified or not. Okay, so but the thing is that here the signal in differential amplifier, it consists of the two input signals are there, and the difference between the two input signals, which may be taken it as an output one. So but the thing is that it is going to be reject the signals common to the both inputs here. The example is that if there is a noise is going to be present, distortion is there, so there itself it is going to be rejecting the signals here. Okay, and also it is not a sensitive for the environmental changes. It may have several applications in the instrumentation, and it is the primary input circuit, and many linear integrated circuits are there, ICs. Okay, so what do you mean by basic difference amplifier or else differential amplifier? You know that it consists of the two identical transistors, that is the T1 and T2, with the identical resistor in their collector circuits. So the two halves of the circuits are perfectly matched. That is the emitter which is connected to the VEE via the emitter resistor RE, that you can call it as a emitter diode, and for biasing the transistors, and the circuit which is going to be energized by giving the power supply 15 volts, plus or minus 15 volts. So here the emitter resistance RE, which is the heart of the differential amplifier. Okay, so this limiting the current which is available to the transistors, and for a constant value of the current, output current is I0. Okay, so the sum of the emitter resistance as well as the for the two transistors, IE1 as well as the IE2, which are equal to the output current here. Okay, that is I0. So here this RE as well as the VE combination, which is going to be act as a constant current source. So let you know about here the working of the amplifier, which may have the two input terminals and the output voltage, which is going to be measured across the two collectors. Okay, the voltage of the equal magnitude of the same priority, which is going to be applied to the terminal 1 as well as the terminal 2. So here you need to take it as a here. This is the emitter diode. This is a RE value. Okay. So this is T1 transistor T1 as well as the T2. This is the first transistor and this is the second transistor T2. And here the voltage is V1 and here the voltage is V2. This is the base one. This is emitter. That is a common emitter configuration, which is so the current which is coming towards the emitter means this is NPN here. Okay. And here these are the two NPN transistors are there. So this is the collector resistance RC, where the collector current is IC1, and here for other transistor T2 transistor, the collector resistance is RC. Okay, so the current which is to be coming out through this is IC2. Okay, so here RE, which is to be both the emitter terminals are to be connected to the emitter resistance here RE, and which is connected to the ground here. Okay, so the collector current as well as the potential difference between these two collectors, this one will be 0. That means the voltage which is common to the both the terminals. Okay, and the terminal do not to be affected by the output voltage. What is the working of this transistor? That means which has the two input terminals here and as well as here. The output voltage which is to be measured across the two collectors here. This is the first one, this is the second collector. The two voltages of equal magnitude and the same polarity. That means a plus, if it is going to be connected plus or minus, same polarities to be applied to the one terminal between the terminal 1 and ground, and other one is the terminal 2 and ground, so that there should be equal changes in the collector current. And the potential difference between these two collectors should be 0. That means there should be a voltage is common for both the terminals. Okay, and the base of the transistor, which is a driver to the positive with respect to the base of the transistor T2, and the current through the T1, which is going to be increases the current through the T2, it is a decreases by an equal amount. One transistor T1, if it is increasing the current, other transistor T2, which is going to be decreases. Okay, why? Because of it has to maintain the constant current I0 value. Okay, now because of here IC1, which is greater than that of the IC. Okay, so the potential difference which is developed between these two collectors, that is the differential input voltage, which may causes the differential output voltage. So this you can call it as a mode of operation, which is a differential input, differential output. So the difference amplifier, which is also be used as in a single-ended output mode. Okay, while we are taking the input is for through the two transistors T1 and T2, but where we are taking the output as for only common for both these two transistors. That is a single-ended output mode. Okay, so let you grounded one of the inputs and the base of the transistor via a small resistor. The positive input of the base T1 results in negative output of the collector. Okay, please understand this. And it is to be acting like a inverting amplifier. So T1 is which is always positive. If the positive input at the base of the transistor results a negative output of the collector. Okay, if you're sending positive and the output should be a negative, so that is a negative inverting amp, and this may be referred as a single-ended input and single-ended output. That is inverting. In this operation, the current of the transistor T1 increases when its base given a positive potential, and to maintain the output voltage, the output current which is constant I0, and the current T2 which is decreases in the same magnitude. So as the consequence of the output voltage, the collector of the T2 will be positive. If we give the input of the T2 T1 and taking the output at the collector T2, it is working as a non-inverting amp. Inverting means only while you are giving a positive input and we are taking the negative at a collector end, that is inverting. But whereas for the non-inverting case, we give the input to the base of the transistor T1 and we are taking the output at the collector of the T2, not T1. Then it is a non-inverting amp. Okay. Next, what are the characteristics of the differential amplifier here? You know that gain means here the output voltage by input voltage. The ratio or the fraction of the output to the input voltage is nothing but a gain of the amplifier. Okay. So let you go for this here where the signals, input signals V1 as well as the V2, which are the signals for the transistor T1 and T2, where the output voltage is V0, and these voltage which is to be measured with respect to the ground here. So the output voltage V0 which is nothing but a AD, okay, A suffix D. That is the AD means differential amplifier gain. A means with respect to V1 minus V2. Or else you can note it down that here AD equals to V0 by V1 minus V2. Okay. So this is the schematic representation of the circuit diagram. So AD is the gain of the amplifier of the differential signal, and it is to be called as the differential gain. If V1 equals to V2, so then that is a 0. V1 minus V2 is V1 equals to V2 means 0 is there. So that there is no gain at all in this case. So that the signal common for both the terminals. That is, there is a noise. So that the amplifier which is going to be rejecting the signal. So in a practical difference amplifier, the output is not 0 when V1 equals to V2. Okay, this means that it does not hold good under practical conditions. The output voltage of practical differential amplifier, which depends not only on the difference voltage, Vd equals to V1 minus V2, but also on the VE, the voltage common to the both the inputs. So, which is called as a common mode voltage. And that common mode voltage Vc, which can be given out the average V1 plus V2 by 2. The output and input voltage relation of the differential amplifier, which can be expressed as V0 equals to AD into V1 minus V2 plus AC VC. Okay. By doing this simplification here, you may get the common mode signal. So what is the ratio? That is the ratio of the differential and common mode gain, CMRR. That is a common mode rejection ratio, rho. That is equals to AD by AC into rho. Okay. So for a good differential amplifier, CMMR in decibels, which may gives you 20 log 10 KD by AC. Approximately equals to 80 to 120 decibel combining equations. So an examination of the above equation, the difference amplifier should be designed to have such a high value for the common mode rejection ratio CMRR, for high values of CMRR are achieved by choosing the transistor so that is for having the large values of HFE and HFE along with the high resistance. So you can go for the examples here. So what are the questions which are to be given out here? Draw the circuit diagram of difference amplifier and explain itself. Give an expression for the gain of the differential amplifier. What do you mean by common mode signal? And define CMRR, common mode rejection ratio, JD by AC, in a differential amplifier. And what should be the magnitude of CMRR for good differential amplifier? Next is the operational amplifier and its characteristic parameter. Characteristics of ideal operational amplifier. And the body, the block diagram of operational amplifier, feedback arrangements, operational amplifier parameters. So we can go for the introduction here. The amplifier, so which has a high inputs impedance, a large bandwidth, and a low output impedance. So to perform a mathematical operations like addition, multiplication, integration, and differentiation, etc. So hence the name is operational amp. Okay, the bandwidth is large and low output impedance, and for the and also one more thing is there at a high input impedance. High input impedance, low output impedance, but bandwidth is large. So these operational amplifiers are widely used in the analog computers and other equipments. Okay, not in a digital computer, which may be used as in analog computers. Hence, it has acquired the name versatile. Okay, operational amplifier, which is a versatile operational amplifier, or simple operational amplifier. Okay. So what is the output voltage of an operational amplifier? V naught equals to A naught into V plus minus V minus. So what is V naught? A naught? A naught is the open loop gain. V naught is the output voltage. V plus and V minus. Sorry. AO is the order for 10 power 5, approximately 10 power 8. So what are the characteristics of ideal operation? Open loop gain A naught infinity. CMR is also infinity. Input impedance ZI is infinity. Output impedance Z0 equals to 0. Zero rate, bandwidth is infinity. Stability, you can see. Bandwidth is also infinity. So here the equivalent circuit for this ideal operational amplifier, which is going to be showing this in figure 2, and which can make up the operational amplifier, which is very useful. So there is no current flows into the operational amplifier. Why? Because of its input impedance is infinite. If input impedance is infinity, the output current should be 0. Okay, please remember this. So ZI means infinity input impedance is infinity, VA is input voltage, V plus and V minus, and the output is A naught into V plus minus V minus. So that output impedance is 0, gain is also 0. Okay. This is the block diagram for the ideal operational amp. And here you can able to observe the characteristics of operational amplifier. The open loop gain is 10 power 5 to 10 power 8, and the bandwidth is also very high. You can able to see that 100 megahertz. Okay, and the input impedance, two op amps which are given out the ranges. One is for the general purpose operational amplifier, and another one is for the MOSFET, metal oxide semiconductor field effective transistor. MOSFET means this one. So here the output impedance, which is also you can able to see that 1 to 10 ohms. Yes. Okay. And the thing is that the CMRR, common mode rejection ratio, that is 80 to 140 decibel here. And the offset voltage and offset current is also given here. Voltage is a few microvolts, and the current should be nanoamperes. Okay, the slew rate is also given out. Then we can go for the operational amplifier block diagram, and here what is inside the IC here integrated circuit. So, however, the users which you are going to be using this operational amplifier, they can feel that it is comfortable when it has some an idea of design, and there should be appreciated in its limitations here. So, the block diagram of the general purpose IC op amp, which consists of differential amplifier, second amplifier, and current to voltage converter is there. Okay. So in the first stage, all types of operational amplifier in the differential amplifier. It has the two input terminals. You can able to see here V plus as well as the V minus, and the difference in the voltage which is applied between the two input terminals. And then this differential amplifier which may converts the voltage into output current or the output voltage. Okay, if you want to get it as a current as well as the voltage, that is going to be converted by this differential amplifier VG. And the second amplifier SA, which may convert these currents or voltage into a single-ended current or voltage. So here there should be a capacitor is there, IV, current to voltage. There itself you can able to observe the capacitor itself. Okay. So here the SA which may convert these currents of voltage into a single-ended current or voltage. That's what you can call it as this is a differential to single-ended converter. You can see here you in differential amplifier you may get it as input as the two terminals as well the output is also two terminals. When it comes to the second amplifier, input which has two terminals are there, but the output is only one, single is there. Can you able to see this? Yeah. So hence it is going to be called as a differential to single-ended converter. This single-ended output current which is converted into voltage by the third amplifier, that is OD. Okay, this one. That's what here only one output voltage which is going to be coming out. So in the final output stage, OD is the output driver, which has the low power amplifier, which is used to boost the power, and it is to be provide the low output impedance. Not in a high impedance, which may be maintained as a low output impedance. Z0 is very less. Next, feedback arrangements. So these are very important. The schematic diagram, you can able to observe here the feedback amplifier, inverting as well as the non-inverting case. If it is minus in the top, that is inverting, whereas the positive terminal, if it is at the bottom case, that is a non-inverting case. Okay, and you may able to observe the here plus VCC as well as the minus VCC also. So it contains it has two input terminals. The terminals which are to be marked as a negative, that is a inverting. If it is marked as a positive, that is a non-inverting. And the plus and minus signs which are indicating that here there is a phase relationship between the input and output voltage. Okay, whether the phase which is going to be giving out 180 degrees or else the 360 degrees, that is going to be depending upon these plus and minus terminals. Okay, so here a positive voltage which is to be applied. Positive means non-inverting. The inverting terminals, they'll say negative output. Okay, that means there is a phase inversion between the input and output. If positive which is given, you are getting a negative, means there is a phase is going to be developed between the input as well as the output. The same voltage which is to be applied to the non-inverting terminal, the result is positive output. But for inverting is, if it is positive, negative you are getting. But whereas for the non-inverting, if it is a positive, you are getting positive. Then the output signal in phase with the input signal. Okay. So the battery and the power supply, which is going to be energize the operational amplifier and the grounded terminals, and the operational feedback arrangement you can see here from the 2.4 A figure, inverting configuration and non-inverting configuration. Okay, if can see that this is a positive one which is grounded, that is inverting configuration. If negative one, if it is through the impedance, if it is grounded, that is non-inverting configuration. Okay, for a closed loop as well as the, what do you mean by impedances here? And you can see here for a closed loop gain of the operational amplifier for inverting configuration, V naught by Vi equals to, that is the gain of the amplifier here, minus Zf by Zi. Whereas for a closed loop gain, AV plus non-inverting, na? Yeah. Here AV plus, here inverting is AV minus. So 1 plus Zf by Zi. That is the case. So what are the parameters you need to find out by using the operational amplifier, which has a set of specific special specifications. Operational amplifier in particular application which is made up of these specifications, and the important parameters, that is open loop gain, that is A naught. The gain of the op amp without any feedback, that is A naught. Okay. And it is also defined as the ratio of the change in the output voltage to the change in the difference input voltage. Okay, delta V naught by delta Vi, which is nothing but a AI change. It is saying that when the change is going to be causes here when AC supply is given. But this is normally specified at DC current. The op amp is very rarely used under the open loop conditions. and the open loop gain, which is significant as it determines accuracy of the operation amplifier with feedback. Next, a common mode voltage gain, that is AC. The ratio of the change in the output voltage to the change in the input voltage, both the input terminals are tied together. That is called AC. Next, CMRR, that is common mode rejection ratio. When two signals are applied to both input as well as the output, single voltage, common voltage applied to the two inputs and tied together, which is called common mode signals. Okay. Some of the examples which are given out, you can go for CMRR, AD by AC value, and it may be expressed in terms of decibels. Okay, dB. Next, bandwidth. This is very large, maximum. So for open loop bandwidth, which is defined as the frequency at which A naught falls by 3 decibels from its maximum value at DC. And it is going to be represent the range of frequencies over which the gain of the operation amplifier reasonably constant. You can see here. For example, if the gain is 100, gain is 100, and its value is 20 log 100, that is 40 decibel. If the gain is 1000, the decibel range is 60 decibel. Next, slew rate. The capacitor in the operational amplifier limiting the rate at which the output voltage can change. Okay, the slew rate, which is defined as the maximum time rate of the change of the output voltage without distortion. This can be specified by volts per microsecond. The slew rate is 1 volt per microsecond. So this can be represented as per with respect to the sine wave, Vp sine 2 pi ft. So Vp is the peak value of the output voltage. F is the frequency. Next, offset voltage VOS. The op amp in general, it gives an output voltage which is called the offset voltage even if the input terminals are earthed here. This is due to the lack of symmetrical mismatch of in the input differential stage of the operational amplifier. So here the seed period during the fabrication process, where the output voltage which may be considered as a rising of output small voltage, input voltage. Next is the bias currents. So the two bias currents, that is IB minus as well as the IB plus, which are I means current here, B means bias current, into the input terminals, even when the input voltage are 0. These are the currents which are used for the bias to the input transistors. So in well, it is going to be balanced the amplifier with equal input impedances. In this condition, the effect of these currents largely cancel here. So the difference between the bias current IB plus as well as the IB minus, which is called offset current, that is in off interest. So the range should be 100 nanoamperes. So finally, summary which may gives you for the operational amplifier, DC amplifier which has high gain output voltage by input voltage, large bandwidth is also there, and high input impedance, low output impedance, which are for operational amplifiers. Where it is going to be using here in mathematical operation. That's what it is named as operational amplifier given to. The main characteristics of any operational amplifier are the loop gain, bandwidth, common mode rejection ratio, flow rate, offset voltage, and offset currents. So the question which may go for this one. Block diagram of operational amplifier and explain function. This also. Characteristics of ideal. This is also most important. Offset voltage, offset current, and CMRR. Next is which is in operational amplifier configurations. In this, you need to know about the simple mode for the ideal operational amplifier, inverting amplifier, how the scale is going to be changing, and the summing amplifier, inverting, non-inverting amplifier, current follower, voltage follower, op-amp integrator, op-amp differentiator. So this is a very important here. Up to where this one. Current, voltage, op-amp integrator, op-amp differentiator. Out of these four, you may expect that there should be one definite question is going to be coming out. Okay. So let you go for the introduction for this under ideal conditions. The voltages at inverting and non-inverting terminals of an op-amp are virtually equal. Okay. When these input inverting as well as the non-inverting terminals are to be equal here voltages, when they are virtually, this is called the principle of virtual equality. And this principle enables us to analyze the different op-amp configurations in simple way. And this leads us to concept of virtual ground and the gain of the op-amp with the feedback network, which is called the closed loop gain. The simple model for the ideal op-amp, the output voltage is V naught equals to A naught into V plus minus V minus. So what are the V plus as well as the V minus? Which are the voltages which you may apply to the non-inverting and inverting input terminals. With the finite values, output it is V naught. A large value of the gain is A naught. So V naught by A, which may gives you V plus minus V minus, approximately equals to 0. And this leads us to give the conclusion that voltages at the two input terminals which are virtually equal. Okay. So this is called principle of virtual equality. It is a powerful approach to the analyze the different operational amplifier form. And the inverting amplifier you can able to see here. Inverting means plus terminal grounded. Okay, we are sending the signal here. This is the RF value, and this is the output. This is the input. This is at input resistance R. Signal is there. You are sending the signal here. but you are taking the signal. But the thing is that here, from positive to negative, where it has inverted here the output voltage, you can see the strength and the signal is going to be enhanced. But the thing is that it is inverted. Okay. Okay. Yeah. So where the point, yes, you can call it as a virtual ground. So this concept, which is useful in many operational amplifiers. For example, two or more resistors which are connected together in a common virtual ground. It may be, they will not be cause any significant voltage coupling between input and sources. But this is because there is an essential no voltage present in this common terminal. So S is the virtual ground. Next, inverting amplifier scale changing. The basic operational amplifier, that is a V plus is 0, V minus is also 0. The current through the RI, which is given out by VI by RI, I equals to, because of according to the Ohm's law, I equals to V by R, I equals to VI by RI. That is, if you are going to be assuming that infinite input impedance, no current flows through the operational amplifier. As a result, the current flows through the RI as well as the RF input resistance and RF. That may be taken as V naught equals to minus IRF. That is, what is the I value? VI by RI. So minus to VI by RI value, which is maybe written as RF by RI. So what is the ideal closed loop gain? That is denoted by capital G, V naught by VI equals to RF by R. So there is a phase inversion which is going to be taken place between the input as well as the output signals. So thus operational amplifier closed loop gain which dependent only in the ratio of the feedback and input resistance. Hence it is used for multiplication. So that's what by applying such an example to it, you may observe that both it can be used for both multiplier and divider. In general, it is called a scale changing amplifier. So virtual ground in detail considering specific example. So this is about the example here. Virtual ground 100 microvolts at S is a virtual grounded. What is the output voltage? Minus RF by RI into VI. Minus RF value is 10K. That is 1000 ohms, 10,000 ohms. By RI is also 10K into 10. So how much you will get? Minus 10 volts. If the open loop gain of the operational amplifier, which is set at 1 lakh, that is which may be produce the output voltage of minus 10 volts. Okay, 10,000. So Vs between the two input terminals, which may gives you 100 microvolts. Micro. So there is a small potential difference of 100 microvolts, which exists between real ground and the virtual ground. So that's what it is to be assumed that virtual ground S is also at a grounded potential. Next is the summing amplifier. You can able to see here summing, which has a 3 input sources VA, VB, VC. the working of the adder configuration, which can be understood by using the concept of virtual equality. And this is also a non-inverting terminal. That means inverting terminal is grounded, that is non-invert. That is V plus is 0. So the resistance for the three terminals, you can see VA is RA, VB is RB, VC is RC. If V and R is there, the output voltage V naught equals to here VA plus VB plus VC. The output voltage which is equal to the sum of the three input voltages, that is 3 into RF. Why? Because of RA equals to RB equals to RC. So if you substitute it there, V naught equals to minus 1 by 3 into VA plus VB. So it is going to be acting like an average circuit. RC equals to minus 1 by 3, RA and RB is minus 1 by 3. So by substituting in it, you may get VA 1 by 3, VA plus 2 VB plus 3 VC. Like that. Next, non-inverting. If you can see inverting, which is a grounded, the non-inverting configuration, V plus equals to VI equals to V minus. That is why, because of this is input in voltage, you are feeding through this. So according to the Ohm's law, I equals to VI by RA. There itself, through the RF, what is the voltage, what is the current which is going to be flowing is, by substituting and by simplifying it, you may get it here. The V naught value which is equals to VI into 1 plus RF by RI. So the thing is that there is no sign change. It may be noted here. The input impedance, you may need to understand that here, which is quite high in this particular case, 3.9. So this is a non-inverting amplifier. What about the current follower? The circuit which may shows the output voltage which is proportional to the input current. Current follower is output voltage which is proportional to input current. If output voltage is less, input current is also less. If output voltage is maximum, input current is also maximum. Okay, that is the case. It is going to be acting as a current to voltage converter. The formula is V naught equals to minus I into RF. So what is the gain of this is, if you consider 10 power 5 and the value is 100 kilo ohms for RF, then the 1 ohm input resistance. And this configuration is an ideal current measuring device, which is useful for measuring very small currents of the order nano amperes and less, nano. Okay, nano range, 10 power minus 9. Current to volts. Okay,